Welcome, everyone, to the third annual LogiCal-LA conference. So let's be clear about what this conference is about, and what exactly is scientific skepticism. Briefly stated by Paul Kurtz, one of the giants of scientific skepticism, a skeptic is one who is willing to question any claim to truth, asking for clarity in definition, consistency and logic, and adequacy of evidence. The use of skepticism is thus an essential part of objective scientific inquiry and the search for reliable knowledge. Carl Sagan said, "Science is a way of skeptically interrogating the universe, with a fine understanding of human fallibility. If we are not able to ask skeptical questions, to interrogate those who tell us that something is true, to be skeptical of those of authority, then we're up for grabs for the next charlatan, political or religious, who comes ambling along." At the heart of this movement is the quest for truth using scientific inquiry. With so much pseudoscience, we need a methodology that can be used to tell us not if a claim is 100% true, but to examine if a claim is most likely true. In other words, to provisionally believe a claim is true until more compelling evidence is presented. Science and scientific research can and will improve our understanding of social issues as well. But there is one issue that is overriding all of these issues. It's climate change. We are placing the human race in a precarious position for future generations as we ignore the prognosis of the world as a whole. As the SGU, Skeptics Guide to the Universe, said several weeks ago on one of their podcasts, this generation is the one who must start to change our planet. It will be much more difficult for the future generations to make a significant change without doubling or tripling the cost to make that change. And most of the current world issues will diminish because all efforts will be placed on saving our planet. We should help other carbon-intensive countries change to a carbon-neutral energy sources. We hope you enjoy the stimulating lectures that our speakers have to offer.
Audible. All right, so now we're going to go straight into outer space. This is probably going to be really a winner. I'm
going to interrupt you for one thing here, Mark. I forgot to mention this. Everybody, stick around after David's talk.
Oh,
got
yeah.
something special for you.
Don't rush out of here. There's prizes. I'm just kidding. Valuable prizes. Anyway, so we are going to bring this gentleman up. David Doody. He is going to talk about Saturn, which I think it's always been since I was a kid one of my favorite places to dream about. So let's give him a round of applause, David Doody. Thank you, sir. Very nice to meet you.
All right, thank you. Hi, everybody. Man, what a great conference. I can't believe it. I'm so pleased to be a part of it now. But I'm not going to be bringing any arguments for rationality, nor do I want to expose any myths or hoaxes. I'm just going to be the entertainment. So before about 1980, most planetary scientists, planetary people, thought that the moons of the outer solar system would be boring, just like our own moon is a dead cinder. Nothing's happening on it. And so they thought all the moons of Jupiter that you can see lined up, if you take a telescope out tonight, you can see the 4 moons of Jupiter lined up. The thinking was they're just old cinders like our own moon. Same with Saturn. The moons of Saturn would just be boring. And then in 1979 and 1980 and 81, the Voyager-1 and 2 spacecraft made quick flybys, but very close. They had TV cameras on them, and they exposed these moons to be enormously diverse, crazy moons with volcanoes and oceans and smooth shells and whatnot. So it's my pleasure to talk a little bit about how we got to Saturn and what the Cassini mission discovered. So let me get to the right square here, and I'll tell you the story. So it all began with Galileo in 1610, when he was using one of the hot new toys that professors were using, this telescope. And he ground his own lens, a little thing about 2 inches, took a look at Saturn, Jupiter, of course, as well, and saw these rings. He had no idea what to make of those rings. Fast forward a century or two, and people were doing the thought, the homework, the math, to tell us that, yeah, it would be possible to fly through the solar system, but it's going to be a matter of achieving enormous speed. Konstantin Tsiolkovsky here gave us the rocket equation, and he showed that to get the speed, enormous speed, you're going to have a large delta V, a change in velocity, to go from 0 to fast enough to leave the gravitation of the Earth, which is about 25,000 miles per hour. And that delta V would depend on, yes, the mass of your rocket before and after firing the engine, but it would depend enormously on the VE, the exhaust velocity of the gases coming out of your rocket. That velocity. And so it was going to be key to have a rocket that could shoot gases out fast and pushed your spacecraft action versus reaction up to enormous velocity. A steam engineer working on a steam engine, Gustave de Laval, in the 1800s, designed a nozzle that had this cross-section of a narrow throat, and at the elevated temperatures and pressures, he was using hot steam, fast forward to hot rocket gases. He designed the throat of the nozzle so that right there at the narrowest point, the gases would hit Mach 1. And when that happens, something magical happens. The exhaust velocity skyrockets, that blue line. And it's at the expense of temperature and pressure, so that helps in your rocket design not to melt or explode your rocket engine. So others, Robert Goddard was key, took that nozzle and built upon it. They designed rocket engines to use liquid fuels, the most energetic chemicals that they could experiment with. And fast forward to when JPL was created with Theodore von Karman's grad students. They were getting kicked out of the labs down in Pasadena because they were making too much smoke and too much noise and explosions once in a while. They came up to the arroyo at JPL up north in the dry riverbed. Well, eventually they gave us things like this. This is a view of the Cassini spacecraft that is as big as a school bus, and it's that big really because inside of it here were some big tanks to contain the propellants. And there are 2 tanks, and you open up valves to feed these nozzles down here, de Laval nozzles, and when you do, they spontaneously ignite and burn the rocket engine. You can shut the valves off, the rocket plume quits, and you can restart it any number of times. Let's see. So on the spacecraft, you can see this large dish antenna that was for communications. You turn the spacecraft and point that to Earth. We also used it for radar imaging of the moons of Saturn. Here are the cameras, optical instruments, spectrometers, cameras, bolted to the side of the spacecraft. So again, you have to turn the whole spacecraft to point the optical instruments. I need to start talking in past tense because we ended the mission almost 2 years ago now. How do you turn the spacecraft? Well, good question. One of the early thinkers, Walter Hohmann, in the early 1920s, said, well, you just put handholds inside of it, and then the people can just grab the spacecraft and twist it around. Well, there are no people, thankfully, on any of the outer planetary system spacecraft. So instead of doing that, I'll let my colleague, the Attitude and Articulation Control Subsystem Engineer, Luis, show how these things work. These are reaction wheels. Turn one of the wheels one way, and the reaction turns your spacecraft. And I missed my... There he is. There's Luis. I've got an electric drill with a big stone, stepping stone, and he's demonstrating how to trade your angular momentum between the wheel and the electric motor and the body of the spacecraft.
Nice. Okay. Wave to the audience.
Thanks, Luis.
Okay.
Okay. So we carried 3 of these wheels and a spare tire as well. Here's a big tank full of helium. Now, why would a spacecraft carry a big tank of helium? Well, obviously, to make it lighter. No, it pressurized the big fuel tanks so that it's a real simple system. All you have to do is open the valves and the pressure feeds the engines. Now, for electrical power, we used the engineering principle called the Seebeck effect. If you have a hot source and a cold sink, the gradient of the hot out to the cold can be used to put a thermocouple in it and generate electricity with no moving parts. For the hot source, well, you see the fins out on the outside, and inside were these pellets of plutonium-238, a ceramic oxide, that just naturally stay hot from the radioactive decay of the plutonium. They'll be red hot for decades. The Voyagers, Voyager-1 and 2, launched in 1977, and their system, it's called a radioisotope thermoelectric generator. Theirs are still going. Voyager is talking to us every day, Voyager 1 and 2. So that's the electrical power source. The spacecraft was all buttoned up inside of this Titan IV Centaur launch vehicle. I took my Bic lighter and I snuck out there and lit it off on October 15th of 1997. And we spent 7 years looping around the solar system, going out to the Saturn world. Now, at launch, we were here at number 1. We separated from the Earth, followed this green track, fired that rocket engine on the spacecraft to fall inward towards the sun, and then we flew by Venus. Flying by Venus gave us a kick to get out to that red arc, which is about the distance of the orbit of Mars. Then we came around, fell back in around the sun, just coasting, constantly coasting, flew by Venus again, flew by Earth, and those flybys gave us the momentum to get out into the outer solar system. Now, Thomas Westbrook, where are you? I do depend on the position of the planets. The gravity assist technique was invented by a student working for the summer at JPL in 1961. And he had a hard time convincing people that it could work, because people would say, you can't get something for nothing. Well, the way it works, a planet going around the sun, say Jupiter, with a whole lot of mass and a distance way, way out there, there's a lot of momentum, angular momentum going around the sun. And you set your spacecraft so it sneaks up behind the planet, and of course, the planet pulls on the spacecraft because of the gravity. But the spacecraft itself is a physical mass, and therefore it has its own little bit of gravity. That's enough to pull on the planet and slow the planet down a little bit. And there's the trade-off. You slow down the planet, Jupiter, tiny, tiny amount, not measurable, but yes, calculable. Slow down the planet, and it gives your spacecraft a big boost. So we depended on that quite a bit. Getting out to Saturn now in 2004, July, we fired our rocket engine for 100 minutes, slowed down and got captured into orbit at Saturn. Spent 13 years orbiting Saturn, every which way, approximately. See these points here and on the other side where they all converge? That's at the orbit of Saturn's big moon, Titan. And we use Titan for gravity assist to shape each of the other orbits. These yellow orbits in here are the final ones that we did. One last flyby of Titan caused the spacecraft to come in, and each orbit, it would go way out to 1 million miles where Titan orbits, and then come in close. We'd fly by just outside of the rings. And we did 20 of those orbits, and then one more Titan flyby brought us in between the rings and atmosphere at the closest approach. After 22 of those orbits, we plowed in to destroy the spacecraft, all used up, into Saturn. Here's my team. I was responsible for the real-time operations team, people that work to send commands up to the spacecraft. There's one of our mission controllers. And to manage the data coming back down, here I'm telling a whole bunch of lies to these visitors. And we worked with the Deep Space Network, a system of huge radio telescopes around the world. In the California desert near Barstow, called Goldstone, in the desert out by Canberra, Australia, and at Madrid, Spain. So as the Earth turns, at least one of these locations can see a deep space spacecraft. Now, our results, I could go 2 or 3 hours on the results, but here's one of the images we took of Saturn. It's a big gas giant, 10 times the diameter of Earth at the equator, 9 times the diameter of Earth north to south. It's fat around the middle. And you can never see this view from Earth. Look at this. Here's the night side of Saturn. From Earth, all you can see is the fully illuminated daylight side of Saturn. The rings, we can see the A ring, the B ring, and the C ring. C ring is these strands. And a division between the A ring and the B ring, which was discovered by Giovanni Domenico Cassini in the 1700s. His name was applied to that division. It's the Cassini division. And we used his name for our spacecraft, the Cassini spacecraft. And look at the sunlight falling through the Cassini division, lighting up the upper blue sky of Saturn. And there's the, the shadow of the A ring, the Cassini division, light pouring through, the shadow of the B ring, and the shadow of the C ring. So you can see they're all different densities. Now, See that? Okay, we'll take a closer look in here. Inside of, I put this in the wrong place. There is a 300-kilometer wide gap. That's actually the wrong one there, but inside of the gap, called the Encke division, is a little moon that orbits inside of the rings, and its name is Pan, and it's only, it's less than 100 kilometers in diameter. But look at that skirt of snow around its equator. That's from ring material coming in from the rings. Out in a different division, the Keeler Gap out here, is another little moon called Daphnis. It's even smaller. It's about 30 kilometers long. And you can see it also has a skirt around its equator from ring material that it's gathered. But you can see the perturbations that it gravitationally induced, these waves before and after. And that led the ring scientists to be able to discover smaller moons embedded in the rings by seeing those wakes. Now, if you're a ring scientist, you'd call this feature a propeller. We went around and got in the shadow of Saturn, and being in the shadow, you could turn the cameras back towards the sun without burning everything out and take an image like this. And this has got so much information in it. When the sunlight is coming towards you through a dusty environment, the dust lights up brightly, like driving on the freeway towards the setting sun, or if you're a morning person, the rising sun. You see all the fine dust on your windshield. Well, the fine dust in this outer ring out here lights up very brightly. You can't see it very well at all from the front, but this ring, it's the E ring. They were named in order of discovery. The A ring, B ring, C ring, D ring is visible. It's dusty and lights up brightly here. The E ring and the F ring could be for scales of the musical notes. But this E ring would disappear in 100 years or so if the geysers on a little moon called Enceladus, and you can see that little moon down here, we'll take a closer look shortly. Geysers are spewing water constantly out of the south polar crevasses on this tiny little moon. That was a huge surprise. And the geysers create that huge ring. Now the F ring is brightest, and that's because it's freshly ground. The particles are being ground right now, finer and finer. And that happens, we'll take a look at the mechanism that makes that happen. There's a little moon that goes out into the F ring and grinds it up. Over in here, there it is. See that little dot? We'll zoom in on it a little bit more. Any ideas what that little dot represents? Earth? Well, let's zoom in a little closer. Ah, yes.
We're running short on time.
Okay.
We're trying to get to Pluto really quick.
Okay. Okay, let's look at the F ring real quick. There's a little moon, Prometheus. It's more eccentric as it orbits the planet. And look at this, there's the shadow of Prometheus, because we took it right at equinox when the sun was edge on to the rings. Here's a movie of Prometheus entering the F ring, doing its freshly grinding act. Went into the shadow of Saturn, and here's Enceladus, up against the sun with the sunlight illuminating those amazing geysers that are going off. This is liquid salt water that very likely show that there's a habitat for life as we know it. At Titan, there are lakes and seas on the surface. This is 10 times as big as Little Enceladus. Dunes, lakes, and rivers, possibly where we could expect life as we do not know it, because the lakes and seas are full of methane and ethane. I would like to invite you to look at this YouTube. It'll tell you all about the Huygens probe that we carried and deployed to Titan. So take a picture of this, or remember to go to YouTube and look for Cassini-Huygens. I'm going to skip that one, and I'm going to go right to the advertisement. Have a look at saturn.jpl.nasa.gov, and I want to finish up by showing a 3-minute video.
A lone explorer on a mission to reveal the grandeur of Saturn, its rings and moons. After 20 years in space, NASA's Cassini spacecraft is running out of fuel. And so, to protect moons of Saturn that could have conditions suitable for life, a spectacular end has been planned for this long-lived traveler from Earth.
Liftoff of the Cassini spacecraft on a million-mile trek to Saturn. We have cleared the tower. Which program is in?
In 2004, following a 7-year journey through the solar system, Cassini arrived at Saturn.
The SOI burn attitude or pointing position. Light up the rockets.
The spacecraft carried a passenger, the European Huygens probe, the first human-made object to land on a world in the distant outer solar system. For over a decade, Cassini has shared the wonders of Saturn and its family of icy moons, taking us to astounding worlds where methane rivers run to a methane sea, where jets of ice and gas are blasting material into space from a liquid water ocean that might harbor the ingredients for life. And Saturn, a giant world ruled by raging storms and delicate harmonies of gravity. Now, Cassini has one last daring assignment. Cassini's grand finale is a brand new adventure. 22 dives through the space between Saturn and its rings. As it repeatedly braves this unexplored region, Cassini seeks new insights about the origins of the rings and the nature of the planet's interior, closer to Saturn than ever before. On the final orbit, Cassini will plunge into Saturn, fighting to keep its antenna pointed at Earth as it transmits its farewell. In the skies of Saturn, the journey ends, as Cassini becomes part of the planet itself.
Thank you.
So let's have another hand for Dave, please.
Thank you very much.
Now, he's a professional, we're going to bring up an amateur cosmologist, astrophysicist. Let's welcome Bob Novella from the Skeptics Guide to the Universe. Come up, Bob. We're going to have a little roundtable discussion for about 10 minutes or so. We'll have 1 or 2 questions, and then we will have to wrap it up.
David, great talk.
So we're going to sit for a minute, huh?
Test check. Is this working? Okay. Should we sit? I've done a lot of research the past week on Cassini. I thought I had a good handle on it when the mission ended, but I really recommend going online, seeing what it discovered. David just kind of scratched the surface today. It was an amazing instrument, probably one of the most successful scientific laboratories ever created. Truly amazing. But I want to start today about the moon, not about Cassini or Saturn, but about the moon. The moon is on everybody's minds, right? It's the 50th,
Earth's moon.
The Earth's moon, yes, the Earth's moon. 50th anniversary, probably one of the most important singular events in human history. First human to walk on another planetary body. So I'm curious, what were you doing on that day? What are your memories, and what did it mean to you?
Oh, when Neil Armstrong took his famous step. Well, my partner and I were in a little apartment. We were still in the Air Force, and we were watching on a black and white TV screen about 6 inches across, I think. I'll never forget that. Yep.
So I've been looking through your career. You worked on Voyager, Magellan, Cassini, of course. So after Voyager 2 did its last flyby, the outer solar system, and was on its way to the edge many years later, to the edge of the solar system, our solar system, there was a party at JPL. Can you describe that party that I wish I could have gone to?
Oh, it was amazing. So Voyager 2 had completed its final planetary encounter. It had no more planets to go visit, and it was soon going to be turning off its cameras. One of the imaging scientists had a famous name, Carl Sagan. He brought in Chuck Berry and a band and gave us a really rollicking way to leave the solar system. Chuck Berry was duck walking his guitar across the stairs in front of the administration building. Everybody was, we weren't drinking. No alcoholic beverages were allowed on the NASA campus at the time, but we were dancing and having a whole lot of fun.
You touched upon search for extraterrestrial life and what Cassini contributed to that, and it really was amazing. If you think that we used to think that the habitable zone of our solar system extended to the Earth, and then we realized that there could have been life on Mars, so we extended that to Mars, and then Europa looks promising, so that extended our zone all the way out to the Jovian system, and then now with Cassini, we know that Titan and Enceladus are also very promising, and it always seemed to me that there's so much to discover in the solar system, so much science to be done, but to me the most exciting scientific discovery would be a discovery of life that either that came from the Earth in panspermia, or something that was completely a unique origin of some sort of microorganisms on these other moons. And it really seems so promising to me. All the ingredients of life are there, organic materials. You've got I think Enceladus probably has salt oceans underneath the crust. Even Titan could have, if not methane-based life, which would be truly alien, since we're carbon-based. But Titan could also have an ocean underneath. So I'm just not sure. I would focus research, spacecraft research, on getting to any of these moons and really looking for life. To me, that would be the priority. But if you could design the next missions in our solar system, robotic or human-led, what would you like to focus on?
Well, I'm not a scientist. I'm an engineer in flight operations, but I have a whole lot of contact with the scientists, and I love the idea that there might be, in our lifetimes, the possibility of discovering life somewhere else within our own solar system. And these moons, they're called ocean worlds now. Europa at Jupiter, that has a warm salt water ocean underneath its thin ice shell, where what could be in this ocean? Here, wherever we look on Earth, wherever there's water, there's something living in it. Even away from the sunlight, the photosynthesis on the surface, you dive into the trenches in the oceans where there are volcanic vents. The hot volcanic vents have their own ecosystem, and worms and other life forms.
And these are life forms that are not based on photosynthesis.
Yeah, they've never seen the sun.
It's
Yeah.
chemosynthetic life. It's not photosynthetic. To me, it makes life even more promising on these ocean
And
worlds.
you have the same thing on Europa and also on Enceladus out at Saturn, the tiny little moon that's giving free samples of its ocean constantly. Europa at Jupiter might also be giving out free samples, having geysers going off. At the limits of detection of ultraviolet from the Hubble Space Telescope, it appears there is possibly a geyser sending water from the saltwater ocean on Europa out into space. There's a spacecraft being designed right now to go to Europa. Actually, it'll be orbiting Jupiter and flying by Europa quickly in and out of the high radiation fields nearby. But it'll be characterizing the icy shell and the ocean of Europa. And if there is a geyser, it'll be clearly visible to the Europa Clipper spacecraft. I just started working a little bit on that program last week, and I'm really excited about that. But there it is, the possibility. There are thermal vents, very likely on the ocean floor at Europa, also Enceladus at Saturn. And so, if life evolves easily and throughout the solar system, we're likely to find it within our lifetimes. That's really exciting to me.
And if you think, oh, this is so far away from the sun, how could life exist? I mean, look at extremophiles on the Earth. We've got microorganisms, bacteria, and archaea that can survive in amazing, incredible environments. Some that could be blasted with radiation and have its DNA scrambled, and then the DNA actually reassembles itself. I think it's called radiodurans is the specific microorganism. Just amazing. We have that here. Certainly have it there. And what I love about those geysers is that you don't have to send a probe to, say, Europa and dig, how many miles down do you have to go to get to the ocean? You could actually just put a probe in orbit and then collect samples, and you could actually find the evidence that we're looking for right in orbit. That's, of course, no guarantee, but that's possible. Right, that's possible.
But you can't send a mission to orbit Europa. You'd be fried in a couple of weeks. Because of the intense radiation belts in near Jupiter. So sure. You orbit Jupiter in a long elliptical orbit and then come dashing through and taking measurements carefully timed to pass by Europa.
So you were one of the lead authors on the basics of spaceflight, the physics. You were teaching about the physics of spaceflight, spacecraft design. Was that a book? Was that an essay? What was the nature of that?
Well, yeah, at first the basics of spaceflight was a website used for training people in mission control. All about how a spacecraft is put together, how they fly, where they can go. And then it became a book. I published it in 2011, and you can get it at paperback. The main book, though, is Deep Spacecraft. It's more of a textbook published by Praxis in 2009. And that has the math in it.
Okay.
Basics of spaceflight has very little math.
And it's still being taught in schools today, I believe, this treatment that you wrote. So given that, I wonder if you share my frustration with chemical rockets. I mean, you displayed on the screen, you showed the orbit, the trajectory that Cassini took to get all the way to Saturn. It had to pass by Venus twice, and then Earth. Imagine you're sending a spacecraft to Venus or to another planet, and it's like, oh yeah, it's coming back to Earth. Wait, but it just launched from Earth. Why is it coming back? Well, that's because of the gravity assist. And gravity assist is a fantastic method to accomplish your goal. But the key, I think, is because they're trying to save money. You could put a lot of chemical fuel in there and use all that, but that would be tremendously expensive. So in order to get there as cheaply as possible, you use the gravity assist. The journey is 7 years. It took 7 years to get there. So, and chemical rockets are fantastic, but I think people don't seem to be focusing enough. They do a little, but not enough on something beyond chemical rockets. If you could design your own rocket, no sci-fi, no FTL, no EM drive nonsense, but modern technology that we have today, how would you design the spacecraft to get to these planets more quickly?
You still can't be in any hurry. If your destination is anywhere in the solar system, it's going to take a long time to get there, no matter what kind of rocket. That said, I drive an electric car. I couldn't wait to get rid of my chemical propulsion car. The minute that a Nissan Leaf became available, I snatched it up. Electric spacecraft engines are very, very much more efficient than chemical rockets are. You still need chemical rockets to separate from Earth and get going, and you'll still want to time your flight according to the positions of the planets to do gravity assists, because there's enormous value there. But if you can leave your little electric engine going, these electric engines, 2 or 3 spacecraft now have demonstrated flying through the solar system using electric engines. They use electromagnetic systems to accelerate usually ions of xenon, heavy atom that's been stripped of an electron, so it has to follow magnetic fields. And you use magnetic fields to accelerate these ions rapidly out the exhaust. And their efficiency is 100 times that of a chemical rocket. And you leave it going for months and months at a time and build up your speed over the time. Just a little bit of acceleration, but over long periods of time. And that can get you out to the planets, the outer planets.
Yeah, it is amazing. You could actually orbit one planet, leave that orbit, and then go to another planet and orbit, something that you cannot do with a chemical rockets, not easily, not on the cheap.
Yeah, the Dawn spacecraft was electrically powered. It had gigantic photovoltaic panels, solar panels, to generate a lot of electricity for its engine. It entered orbit around the asteroid Vesta, orbited Vesta for a long time, characterized Vesta's surface and interior. You can measure the interior by measuring the gravitational field and imaging the body to see the size. And once you know the size and the gravity of the object, you get the density, and that gives you clues to what's inside. So anyway, Dawn did that at Vesta and then fired up its electric engine again and went on to another body. It orbited the first asteroid ever discovered, Sirius, the largest one. Did the same thing there.
So I think we're out of time. Bruce? David, thank you very much.
Hey, thanks everybody. It's been a real pleasure.